Welcome to AI Paper Podcasts, the show where we really dive deep into the latest AI and tech research papers.
Glad to be here.
So today we're tackling a really important paper, one that's definitely stirring up discussion. It's all about the difference between AI agents and agentic AI.
Yeah, you hear these terms everywhere now, right?
Exactly.
Yeah.
And this paper, well, it aims to bring some much needed clarity. It gives us a kind of structured taxonomy, which should be super helpful for AI researchers, ML engineers, basically anyone trying to keep up.
Totally agree. And for anyone just catching the highlights, maybe listening on the commute, here's the quick version. AI agents, think of them as autonomous software programs built for specific jobs. They often use tools to help out. Specialized problem solvers, basically.
Okay.
Agentic AI, though, that's more about the bigger picture. It's systems made of multiple AI agents all collaborating, talking to each other to tackle much more complex, maybe multi-step goals.
Right, the collaborative aspect.
Exactly. So the paper digs into how both are built on things like LLMs and LIMS, large language and image models. It looks at how their architectures are changing, the different ways they're being used, everything from customer service bots to like coordinating robot teams.
And the limitations too, I imagine.
Oh yeah, it definitely covers the limitations. A big one is causal reasoning, understanding why things happen, and it points towards some potential solutions. So our mission today is really to unpack all of that, pull out the key insights for you, our technical listeners, to help you stay right at the cutting edge.
Okay, let's jump in. The paper starts by laying some groundwork, looking back at some, foundational ideas.
It does, yeah. And what's pretty interesting is it connects to work from folks like Castelfranchi and Ferber from, way before this whole deep learning explosion.
Really? How's that relevant now?
Well, Castelfranchi's work was on social action, the sort of mind aspect in social settings, how individuals act, their intentions, and how that scales up to collective stuff, like delegation, adopting goals from others. It sounds philosophical, but it's surprisingly relevant when you're trying to build AI systems that need to cooperate.
Huh, okay. And Ferber?
Ferber focused on multi-agent systems, MAS. He gave us a framework for thinking about individual agents, their autonomy, how they perceive their environment, how they communicate. This early focus on what makes an individual agent tick within a larger system, that directly informs how we design modern agents that need to work together effectively.
So it's not like these ideas are brand new then?
Not entirely, no. They're being sort of rediscovered and turbocharged with Tay's AI.
Got it. So bringing it to today, how does this paper define an AI agent specifically?
Okay, so the paper defines them as instantiated AI systems, specifically built for goal-directed behavior. The key thing here is distinguishing them from your general-purpose LLMs. And think of it like this. An AI agent has a clear purpose from the get-go. It has a certain amount of freedom, autonomy to figure out how to achieve that purpose, and it stays focused on that task. An LLM, even a really smart one, is more reactive. It waits for a prompt, does its thing, then waits again.
Okay, makes sense. And the paper highlights some core characteristics. Figure 4, I think?
Yeah, figure 4 lays out 3 key ones. First, autonomy. The ability to act on its own, with minimal human hand-holding. That's vital if you want to scale things up.
Right.
Second, task specificity. They're usually built for narrow, well-defined jobs. That lets you optimize them really well for things like, say, scheduling or running specific database queries or filtering information. High performance in a specific niche.
And the third?
Reactivity and adaptation. They need to respond to what's happening around them. User commands, changes in software state, API responses, whatever. And some can even adapt their behavior based on feedback or new information they get.
So what's actually powering these agents? What gives them these abilities?
That's where the foundational models are key. Large language models, your GPT-4s, LLMs, and also large image models, LIMS, like SLATE or BLIP2. The paper stresses these are the core reasoning and perception engines.
Okay, so LLMs for language, LIMS for vision.
Basically, yeah. LLMs handle the natural language stuff, understanding requests, planning actions, talking back in a human-like way. LIMS let the agent see and understand the visual world.
Can you give some examples of how they're used in agents?
Sure. The paper mentions customer support agents. An LLM can understand a customer's complaint, even if it's messy, and then use tools to query, say, a CRM or a knowledge base to find the right answer.
Okay, that's a common one. What about LIMS?
For LIMS, Figure 5 has this cool example of an autonomous drone in an orchard. It uses its vision, powered by a limb, to spot diseased fruit on trees. When it finds something, it can automatically trigger an action, like alerting a ground crew or marking the location.
That's pretty neat, combining different tech.
Exactly. And in more complex robots, you see this fusion all the time: computer vision, SLAM for navigation, reinforcement learning for decisions. And even NLP and LLMs are used to translate our high-level commands into concrete robot actions. It's about using the best tool for the job.
And it feels like getting access to these powerful models is easier now, which must be driving things forward.
Absolutely. The paper points this out: the rise of cloud APIs from OpenAI, Hugging Face, Google. It really lowers the barrier to entry for building these things.
Right.
And then you have agent frameworks like LangChain or AutoGen. Think of them as like development kits. They provide the plumbing, the structure to help you connect these models together and build actual working agents more easily. It makes it much more modular.
The paper also talks about generative AI, kind of as a precursor to agentic intelligence. What's the main difference there? Why isn't generative AI already an agent?
It boils down to autonomy and proactive goal seeking. Generative AI is amazing at creating content based on prompts, text, images, code, whatever. But it's fundamentally reactive. It generates, then stops.
Waits for the next instruction.
Precisely. Even with huge context windows like in GPT 4.1, the paper argues they still lack that self-initiated drive. They don't wake up and decide, I need to achieve this goal today, and then figure out how to do it over multiple steps. They need that external prompt.
Okay, so generative AI is the foundation, but LLMs are the real engine pushing us towards these more independent AI agents. How does that engine work here?
Exactly. The paper really emphasizes that LLMs like GPT-3, Llama, and others, their ability to go beyond just text generation to do things like plan adaptively, make decisions on the fly, understand and act within an environment, that's the key enabler for autonomous agents. They're the cognitive core.
The brain of the agent.
Yeah, you could say that. They take a high-level goal, break it down into steps, figure out if they need to use a tool like search the web or run some code, and manage that whole process to get the job done.
And systems like AutoGPT or Baby AGI, they're examples of this.
Spot on. Those systems use models like GPT-4 in this sort of continuous loop. Give it a goal, and the LLM plans, acts, maybe calls an API, sees what happens, and then plans the next step based on that result. It's this iterative cycle plan, act, observe that lets them tackle complex stuff without a human intervening at every step.
You mentioned tools again. How does an agent actually use an external tool? Like, what's the mechanism?
Right, so tool augmentation is crucial because LLMs have limits, right? They can hallucinate, their knowledge gets outdated. Tools let them access real-time data or perform actions they couldn't otherwise.
So how does it work? Does the LLM just decide, I need Google?
Kind of, yeah. It first recognizes it needs something external. Then it has to generate a call to the right tool, often in a specific format, like JSON or sometimes just natural language the tool understands. The tool does its thing, gets a result, and that result is fed back into the LLM's context.
So the LLM sees the tool's output.
Exactly. Then it can process that new information and decide what to do next. The React framework reasoning and acting is a really good example of this tight loop between thinking, using tools, and acting.
And the clearest example for most people is probably ChatGPT using Bing search, right?
Totally. Figure 6 in the paper shows a news query agent doing just that. It needs current info. It triggers a web search, digests the results, and uses that to answer the user. It expands what the agent can reliably do massively.
Makes sense.
And the paper lists others too, like AutoGPT for market analysis, GPT Engineer for coding help, Paper QA for digging through research papers, all built on this idea of augmenting the LLM with tools.
Okay, great. So we have AI agents, autonomous, task-specific, often tool-augmented. Now let's level up to agentic AI. What's the big shift here?
Agentic AI comes into play when the problems get really complex or need lots of steps, or, crucially, require a collaboration that one single agent just can't manage well.
So it's about handling bigger, messier problems.
Exactly. And the paper highlights a few key things that enable this. One is goal decomposition, breaking down a huge goal into smaller subtasks. Another is more sophisticated reasoning and planning over a longer timescale.
And communication, you mentioned that earlier.
Absolutely critical. Agents need ways to talk to each other, share information. Could be through messages, could be through some kind of shared memory space. And also reflective reasoning, the ability to look back, learn from mistakes, maybe even critique each other.
The paper uses a smart home analogy in Figure 7, which seems helpful. Can you walk us through that?
Yeah, it's a good one. So the AI agent is like a standalone smart thermostat. It does one job, manage temperature. Maybe it learns your preferences, but it's isolated.
Yeah.
The Agentic AI is the whole smart home ecosystem. You've got multiple specialized agents, one watching the weather, one tracking your schedule, one optimizing energy use, one handling security. They all talk to each other, share data, and work together towards a higher level goal, like a comfy, safe, efficient home.
So it's the interaction and coordination that defines agentic AI.
Precisely. It's intelligence emerging from the collaboration of specialized parts, not just one smart device doing its thing.
That clarifies it nicely. And Table I in the paper breaks down these differences more formally.
Yes, Table I is super useful. It compares AI agents and agentic AI side by side on things like their basic definition, how autonomous they really are, the task complexity they handle, how they interact, memory, planning capabilities, even failure handling.
And agentic AI generally scores higher on complexity, interaction, planning.
Generally, yes. Higher autonomy and coordination, handles way more complex tasks via that decomposition, needs more advanced communication, manages bigger contexts, uses more intricate planning, and often has built-in ways to deal with failures in one part of the system without bringing everything down.
Gotcha.
And the paper actually has a whole bunch of other tables too through IXMA, I think, that go even deeper into this taxonomy, comparing generative AI, AI agents, and agentic AI across all sorts of dimensions, cognitive, architectural, functional scope, you name it. It's very thorough.
So architecturally, how does an agentic AI system differ from a single AI agent? What gets added or changed? Figure 8 touches on this.
Right. Figure 8 shows the evolution. Your basic AI agent architecture usually has perception, some kind of reasoning module, maybe rules, maybe a workflow engine action selection, and some simple learning or memory. Think React's loop.
Okay, standard components. What does agentic AI add?
Several key things. First, often an ensemble of specialized agents. Instead of one agent doing everything, you break it down. MetaGPT is a cool example, modeling a software company with agents for different roles, product manager, engineer, QA.
So specialization and interaction. What else?
More advanced reasoning and planning, maybe recursive reasoning, breaking tasks down and farming them out, using techniques like chain of thought or tree of thoughts to explore options more deeply and replan if needed.
And memory becomes more important.
Definitely. Persistent memory architectures are crucial. You need ways to store knowledge long-term, across interactions, maybe shared between agents. Think episodic memory for events, semantic for facts, vector databases for similarity. Autogen's scratch pads are kind of like this shared memory idea.
Okay, and one more?
Orchestration layers or meta agents. You often need something overseeing the whole process, coordinating the specialist agents, managing who does what when, maybe resolving conflicts, like ChatDev's CEO agent directing the developer agents.
That makes sense. All these advancements must open up more complex applications. Let's talk about those. Where are AI agents being used effectively now? Figures 9 and 10, Table X?
Yeah, loads of areas. Customer support automation is huge, using retrieval-augmented LLMs with vector stores. Think Salesforce, Einstein, Intercom, Fin. They answer questions, pull info from internal systems.
Right. What else?
Internal enterprise search, like Notion AI, helping employees find company info. Email filtering and prioritization Outlook. Superhuman use AI to sort your inbox. Personalized recommendations, obviously Amazon, YouTube, Spotify, analyze your behavior. And even basic data reporting tools like Tableau Pulse or Power BI Copilot let you ask for data insights in natural language. Plus things like autonomous scheduling assistance, X.AI, Reclaim AI managing calendars.
Okay, so lots of practical focused automation. Now, what about the more complex collaborative agentic AI applications? Figure 11, Table X's.
This is where it gets really interesting. Intelligent robotics coordination is a big one. Think automated warehouses with multiple robots collaborating, or that drone example in the orchard, but scaled up multiple drones, maybe ground robots, all coordinated by a central system managing tasks, sharing a map via shared memory, adapting on the fly.
Okay, robotics makes sense.
What else? Collaborative medical decision support. Imagine specialized agents helping in an ICU, one analyzing vitals, one retrieving patient history, one suggesting treatment options, all coordinated and presenting info to doctors. Or radiology triage.
High-stakes stuff.
Definitely. And adaptive workflow automation in business. Complex processes like legal review or handling cybersecurity incidents. You could have agents for threat classification, log analysis, compliance checks, mitigation steps, all coordinated by an orchestrator, maybe learning from past incidents. Platforms like Multion or Cognosys are heading in this direction.
It sounds incredibly powerful, but I'm guessing it's not all smooth sailing. The paper discusses challenges too, right? Let's start with the single AI agents. What are their main limitations? Figure 12A.
Absolutely. A fundamental one is the lack of deep causal understanding. They're great pattern matchers, but often confuse correlation with causation. That makes them brittle when things change unexpectedly.
The why problem again.
Exactly, and they inherit all the LLM weaknesses. Hallucinations, being sensitive to prompt wording, sometimes shallow reasoning, high compute costs, static knowledge unless updated, potential biases from training data.
Right, the usual LLM suspects.
Plus, many agents still have fairly limited autonomy and proactivity. They aren't truly self-starting in many cases. And they can struggle with really long-term planning or recovering gracefully when something goes wrong mid-task.
And safety concerns.
Big time. Especially for critical applications. Their behavior isn't always predictable, and verifying they'll always do the right thing is really hard right now.
Okay, so those are challenges for individual agents. When you network them together in Agentic AI, do these problems get worse? Figure 12B.
They often do, yeah, and new ones emerge. That causality problem, it gets amplified. Imagine multiple agents making decisions based on correlations, influencing each other. You can get cascading errors that are incredibly hard to trace.
Coordination issue.
Major ones. Keeping multiple agents aligned on the goal, ensuring they have the same understanding of the situation, the limits of their communication protocols, fighting over resources. These become significant bottlenecks.
And predictability goes down.
For sure. Emergent behavior is a huge challenge. You put these agents together, and the system might do things you never intended, get stuck in loops, deadlock. And figuring out why an LLM-based agent did something is hard enough. Debugging interactions between many of them is way harder.
Sounds like a nightmare to scale and debug.
It can be, yeah. And that ties into trust and explainability. How do you verify a multi-agent system is safe? How do you explain its decisions? We don't have great tools for that yet.
Security must be a bigger issue, too.
Definitely. More agents, more communication lines mean a larger attack surface for things like prompt injection or manipulating how agents coordinate.
Ethical challenges.
Amplified as well. Who's accountable when a multi-agent system makes a mistake? How do you prevent biases from spreading and reinforcing across the system? How do you ensure the collective goal aligns with human values? Big questions.
Wow. Yeah. Go.
And finally, the paper points out the foundations are still, well, immature. We lack standard architectures, robust theories, especially around that causal reasoning piece for multi-agent setups.
So a lot of challenges. But the paper must offer some hope. What are the potential solutions or future directions it highlights?
It does. It points to several promising areas. For reasoning and planning, integrating explicit causal models, using better planning frameworks. Tool use function calling is seen as vital for grounding agents in reality, both single and multi-agent.
The agentic loop.
Yeah, that iterative cycle of reason, act, observe, refining that is key for adaptation. Better memory architectures, episodic, semantic, vector, are crucial for holding context and enabling longer-term planning, both individually and collectively.
And for the multi-agent coordination.
More sophisticated orchestration, definitely. Role specialization helps break down complexity. Mechanisms for self-critique and inter-agent evaluation could improve robustness agents checking their own work, or each other's.
What about managing the prompts?
Programmatic prompt engineering pipelines, ways to automatically generate good prompts consistently, could help with scalability and reliability. And we desperately need better evaluation metrics and benchmarks to actually measure progress objectively.
And monitoring ethics.
Crucial. Better monitoring, auditing, and explainability tools are needed for transparency and trust. And developing clear ethical governance frameworks is non-negotiable as these systems get more autonomous. Domain-specific systems might also be a path forward. Specializing agents for particular industries could improve performance.
Okay, lots of avenues there. The paper also mentions something called the Absolute Zero Framework, AZA-DI. Sounds intriguing.
Yeah, AZR is a more forward-looking idea. The concept is agents learning without needing massive data sets beforehand. Instead, they learn through self-play, trying things out and getting verifiable feedback like, did the code compile? Did the robot reach the goal?
Learning by doing, essentially.
Kind of, yeah, but in a very structured, self-driven way. It could potentially lead to self-evolving systems, agents that learn and adapt in the wild without constant retraining. It's still research, but a potentially transformative direction for achieving truly autonomous intelligence.
Fascinating stuff. This has been a really thorough exploration of this paper, distinguishing AI agents from agentic AI.
Yeah.
Let's maybe recap the absolute core takeaways.
Sure. So, key points. AI agents are autonomous, task-focused problem solvers, often using tools. Agentic AI is about collaborative ecosystems of multiple agents for complex tasks. Both heavily rely on foundational models like LLMs and LIMS. Applications are growing rapidly, but major challenges remain, especially around causal reasoning, coordination, safety, and explainability in these complex systems. This paper's taxonomy is super valuable for guiding research and design moving forward, and solutions involving better reasoning, tools, memory, and orchestration show promise.
So here's maybe a final thought to leave everyone with. As these agents get smarter and more interconnected, weaving themselves into more parts of our lives, how do we actually ensure they operate safely, reliably, ethically, especially in these complex, multi-agent scenarios?
That's the million-dollar question, isn't it?
It really is. And what role will potentially radical ideas, like that absolute zero framework, play in getting us closer to truly autonomous, trustworthy AI? Definitely food for thought.
For sure.
If you want to dig even deeper, we highly recommend checking out the paper itself. Thanks for tuning in to AI Paper Podcasts.
Thanks, everyone.